So in this case, there is a boy with chronic pain for over 3 years, and he has saw 70 doctors over these 3 years, but still cannot find the correct diagnosis. And his mother finally input relevant symptoms and the MRI notes into the ChatGPT. And finally, it's ChatGPT to help to find the correct diagnosis. So what exactly the performance of current large language models on complex diagnostic reasoning tasks? Oh, okay. Yeah, I'll start recording now. So there is one paper recently published in JAMA. They investigate the current SOTA generative AI like GPT-4's performance on the complex cases from the NEJM, and they show the correct diagnosis in its differential of GPT's performance is 64% accuracy, and the top diagnosis accuracy is 39. And recently there is Google released the MedGermany models, and they further evaluate MedGermany's performance on more cases from the NEJM. And MedGermany outperformed GPT-4 and achieved the SOTA performance, achieved the top 1 accuracy of 30% accuracy, and the top 10 accuracy of 72. So according to these empirical studies, we can show that although existing SOTA large language models demonstrate promising performance on this complex diagnostic challenge, it still has big room to improve their performance. What's the way to improve the performance of large language models in medical application? The key is to using comprehensive medical data like literature, medical book, clinical notes, and guidelines. There are 2 research directions, actually. One research direction is to improve the performance of commercialized large language model with the closed source instruction fine-tuning and or using the retrieval augmentation. However, the key challenge or disadvantage of this research line is that the closed source nature of the commercialized large language model, you cannot get the weight of these models and make it unfeasible to adapt the model into different medical scenarios. So to deal with this issue, there are many studies to develop the open source large language models. Among all models, LLaMA is the most representative and effective open source large language model in the general domain. And there are many studies show that by continual pre-training or fine-tuning the LLaMA 2 model with the domain-specific data can actually improve their performance in these specific domains. Therefore, there are many medical large language models have been proposed, like the PMC LLaMA paper and the Meditron models. However, most existing these medical large language models are only focuses on the biomedical domain, and they only evaluate on the QA task. Only a few exceptions focuses on the clinical domain. Qianqian GPT developed by the Florida University and the clinical LLaMA model are 2 exceptional. Qianqian GPT is a model continue pre-training from the scratch with clinical notes, and it has shown comprehensive performance on the various clinical NLP tasks. However, without the instruction fine-tuning, it has limited zero-shot ability. Clinical LLaMA model is another medical LLM continue pre-trained with LLaMA 2 7 billion with very limited clinical notes from the Mimic 4, and they only focus on evaluation the classification task. So overall, current existing medical large language model either focuses on biomedical or clinical domain and evaluates on the very limited scope. So to address this issue, our aim in this study is to develop powerful medical large language models so as to achieve our long-term goal of developing capable AI for medicine. So in this study, we propose a novel medical large language model family called Me LLaMA based on LLaMA 2. And it has the chat version and the foundation version in both 70 billion and 13 billion. It's developed by continual pre-training and instruction fine-tuning of LLaMA 2 model with comprehensive medical data. So to support the model development and evaluation, we propose a novel domain-specific data suite, including the current largest scale of continual pre-training data with 129 billion tokens, and the novel medical instruction turning data with over 200K instruction turning sample. We also propose a novel evaluation benchmark with 6 critical medical NLP tasks. And our evaluation on this proposed novel benchmark have shown that Me LLaMA model outperforming all existing open source medical large language models and even GPT-4 in several tasks. So this figure shows the overview of our study. We start with continue pre-training the LLaMA 2 model with the mixed pre-training data so as to develop the Me LLaMA foundation model. So to further improve its instruction following and zero-shot ability, we further conduct the instruction fine-tuning using the novel proposed in medical instruction turning data. And we focus on evaluate the supervised learning ability of the Me LLaMA foundation model. So we conduct the task-specific fine-tuning by separately fine-tune the Me LLaMA foundation model with the training set from each evaluation data. And for the chat version model, we focus on evaluate its zero-shot and few-shot ability. I'll next introduce more details of each part. So regarding the continual pre-training, we use the LLaMA 2 13 billion and 70 billion as the backbone. And our mixed pre-training data include data sources from biomedical, clinical, and general domain. So we use over 3 million PubMed-centered full articles and over 50 million abstracts from PubMed. Regarding to clinical domain data, we use the clinical notes from MIMIC-4.3 and MIMIC-CXR. To avoid the knowledge forgotten issue during the continued pre-training, we further mixed a small portion of general domain data from the red pajama data. It's a replicate of the pre-training data used by the LLaMA 2 models. So the data ratio of the biomedical, clinical, and general domain data is 15:1:4. The pre-training objective is actually the next token prediction. The aim is to predict the next correct token based on the previous token of the input text. We set the training epoch to 1 and the learning rate to 1E-5. We use the computational resources from University of Florida supercluster. We use 168-100 GPU to support our continued pre-training, and it takes over 700 hours to complete the 1 epoch continued pre-training of 70 billion model. To further improve the instruction following and zero-shot ability of the Me LLaMA foundation model, we further fine-tune it with the medical instruction turning sample we build. So we build over 200K instruction turning sample from diverse data sources, cover 3 domains, including the biomedical, clinical, and the general domain. Our fine-tuning process is conducted with 3 epochs, and we set the learning rate to 1E-5. We use the LoRa-based parameter efficient fine-tuning rather than the full parameter fine-tuning. And we also use the deep speed package to support the parallel instruction turning. This figure shows the examples of our QA instruction training data in the Hugging Face data format. So it's basically input the prompt and the question. The output is the gold standard answer to the question. This table further shows the details of our instruction training data. For the general domain data, we use 3 commonly used conversation data, including Alpaca, Dolly, Shell GPT. For the biomedical domain data, we use 2 real-world conversation data from the website. And we also use the open source medical instruction training data released by existing study. We use several QA datasets, and we propose some novel instruction training pairs based on the PubMed central articles to support the summarization, next sentence generation, keywords prediction task. For clinical domain, we also build novel instruction training pairs based on the MIMIC 3 and MIMIC 4 datasets with the task of QA, summarization, classification, and mortality prediction. So the whole fine-tuning process is conducted on 8 A100 GPU, and it takes over 140 hours to complete the 3 epoch instruction fine-tuning. As we discussed before, to evaluate the supervised learning performance of the Me LLaMA foundation model, we further conduct the task-specific fine-tuning with the training data from the each training sample from each evaluation dataset covered in our evaluation benchmark. We set the training epoch to 3 for datasets with training epoch with training sample larger than 10K, and for the training set with the training sample less than 10K, we set the epoch to 5, and we set the learning rate to 1E-5. And finally, these fine-tuned models will be evaluated in the test set for each data, from each data. This figure shows the details of our evaluation benchmark. So our evaluation benchmark covers tasks 6 critical medical applications from both clinical and biomedical domain, and it includes 12 datasets. We include tasks of like QA, name entity recognition, relation instruction, classification, text summarization, and natural language inference. So for most tasks, we use the accuracy and the macro F1 to evaluate performance. For text summarization task, we use the commonly used metrics like Roche and the BERT score. We compare Me LLaMA's performance with various large language models in 3 different settings. So in the zero-shot setting, we compare Me LLaMA with commercial large language model, including GPT-4 and ChatGPT, and also some other open source large language model with instruction following ability, including Llama 2 13 and 70 billion chats, PNC Llama 13 billion chats, Medicine 70 billion, MedAlpaca 13 billion, and Alpaca 13 billion. In the few-shot setting, we compare Me LLaMA with the Medicine 70 billion model, the current SOTA medical open source medical large language model. In the supervised learning setting, we also compare with the commercial large language model GPT-4 and ChatGPT, and also some other open source large language model, including Llama 2 Medicine and the PMC Llama 13 billion. These 2 figures shows the performance of various models in the zero-shot learning setting. So the left figure shows the performance of 13 billion model, and we can see the Me LLaMA 13 billion chat model actually achieved the best performance in 9 out of 12 datasets. And the right figure shows the performance of 70 billion model. Me LLaMA 70 billion chat achieves the best performance in 11 out of 12 datasets. And we also compared the performance between the 13 and the 70 billion chat, we found that the Me LLaMA 13 billion chat version model's performance actually has outperformed the LLaMA 2 70 billion chat in half of datasets. This figure further compares the performance of Me LLaMA and the Meditron 70 billion model. Since Meditron model doesn't conduct the instruction fine-tuning, so they have limited instruction following ability. So to make a fair comparison, we compare the performance in the few-shot learning setting, and we can see Me LLaMA still achieves best performance in 11 out of 12 datasets. These two figures shows the performance comparison of different models in the supervised learning setting. Among 13 billion model, we can see that in this figure, Me LLaMA 13 billion foundation model achieves the best performance in 10 out of 12 datasets. And the right figure shows Me LLaMA 70 billion model achieves best performance in 9 out of 12 datasets. So let's compare the performance of Me LLaMA models with the current SOTA conventional large language model GPT-4. We compare the performance in both zero-shot and the supervised fine-tuning setting. In the supervised learning setting, we can see that the Me LLaMA model outperformed GPT-4 on 5 out of 8 datasets and outperformed ChatGPT on, say, 7 out of 8 datasets. In the zero-shot learning setting, Me LLaMA model outperformed ChatGPT on 5 out of 8 datasets, but it underperformed GPT-4 on 7 datasets. However, considering the significantly smaller parameter size of Me LLaMA model when compared with the GPT-4 model, we think the current results already proves the impressive performance of Me LLaMA models on diverse medical application. Let's further investigate the impact of continual pre-training and instruction tuning. So in this table, we will focus on compare the performance of the Me LLaMA foundation model along with its backbone model, LLaMA 2 model, to see the effectiveness of continual pre-training. And we'll also compare the performance of the Me LLaMA chat version model along with its backbone model, Me LLaMA foundation model, to see the effectiveness of instruction fine-tuning. So it clearly shows that both continual pre-training and instruction fine-tuning can improve the model's zero-shot performance significantly. And when compared with the LLaMA 2 model, so the Me LLaMA foundation model has the performance improvement from 0.5 to 55%. And compare with the chat version model and the foundation model, so the Me LLaMA chat version model has the performance improvement from 3.7% to 41.9%. So based on our Me LLaMA chat version model, we developed the online chat demo where you can interact with the Me LLaMA chat model by input natural language text. So this video shows an example of how we interact with the chatbot. Here we input a question. So what's the potential side effects for an asthma patient taking prednisone? Yeah. So it shows some reasonable side effects like weight gain, mood changes. So we will further interact with it by asking whether the side effects can change with the period of taking prednisone. So yeah, it further shows the long-term side effects like kidney stones. So to facilitate future research, in this area, we will release all our datasets and models in this open source GitHub repository. Then I would like to discuss some findings during our model development. Firstly, regarding to the model performance, in the zero-shot learning setting, we noticed that almost all models, including GPT-4, has very low performance in some certain tasks like NER relation instruction and the EMRQA datasets. So after manually evaluate and check the prediction files, we found that this is caused by these models cannot follow instructions correctly. And this also lead to significant challenge for our automatic evaluation process. So we consider that future research can further improve the prompt to improve the performance of models on the zero-shot setting. On the supervised learning setting, we found that the Me LLaMA model's performance has already the comparable or better performance than the traditional SOTA methods in various tasks based on pre-trained language models like PubMed, BERT, or BART. But we do find that, and also some existing studies show that current some evaluation metrics used in the text generation task like text summarization is not very effective to evaluate the performance of large language models. So to develop advanced medical large language models, we found that the high quality and the diverse pre-training data is very important. And it's also very important to mix the general domain data to avoid the data knowledge forgetting issue. But the optimized data ratio between the general domain data and the medical data is actually not very straightforward to determine, and it requires empirical study. So currently the PMC LLaMA model, they use the biomedical domain and the general domain data ratio of 19:1. Meditron uses the 19:9:1. So both of them has the knowledge forgetting issue in the general domain based on our evaluation. And the Me LLaMA model use the data ratio of 4:1. It alleviates the data, not the knowledge forgetting issue, but we cannot guarantee this is the optimized, this is the best choice of the mixed data ratio. So regarding to the pre-training and the fine-tuning, we found that the pre-training process is very computational heavy, and the fine-tuning requires less computational resources when compared with pre-training. It only requires like A100 GPUs to support the fine-tuning process. So if you have limited computational resources, we think fine-tuning will be a better choice. And our evaluation and discussed before already show that the fine-tuning, only based on fine-tuning, the model's zero-shot ability can already be significantly improved. Regarding to the usage of Me LLaMA models, we think the foundation model is more suitable for supervised learning, where you have enough annotation data, and the track version model is more suitable for the zero and few shot setting, where you have limited labeled data. Regarding as for the 70 billion and 13 billion model, so we think 13 billion model is a better choice if you have very limited computational resources, because we found that the 13 billion model actually has comparable performance to the 70 billion model in most cases. Finally, I would like to discuss some key limitations of our Me LLaMA models. Like all existing large language models, it has the problem of factuality. It can generate responses, fake responses, or unfaithful responses. So to mitigate this issue, we may investigate the retrieval augmentation or reinforcement learning from human feedback method to alleviate this issue. The second issue is the limitation of our model to handling long context. Due to the limitation of our backbone model, LLaMA 2, so the maximum input length of our model can handle is 4K. So in the future, we will investigate the long context extending methods like long LoRa to effectively revise the positional embedding of each transformer layer to effectively extend the model to handling longer inputs, like up to 12,000 tokens. Yeah. So finally, I would like to express my acknowledgement to our team member and our collaborators from the University of Florida. Yeah, so this is all my presentation, and I would like to answer any possible questions. Thank you. Thank you for your attention.
Thanks for the talk. It's great. May I ask, has Meta open sourced their training data sets?
No, so they released they have detailed illustration of the LLaMA 1 models, but in the LLaMA 2, there is no very detailed illustration of the training data they use. And the LLaMA 3, they also doesn't mention the training data they use, but it's highly probably the LLaMA 3 will use the overlap training data like the LLaMA 2. And the red pajama data they claim in their website that is kind of replicate. It has very similar distribution to the pre-training data used the LLaMA 2. So this is why we use the red pajama, sample the small portion of data from the red pajama data. Yeah, thank you.
Mixing in the open domain data to try to keep the performance high, it can be inefficient if the ratio starts to get high, right? Because you're
yeah,
on what it's already trained on. Would it be possible maybe to use like KL divergence in the loss function versus the original model, so you can keep the parameters close without going through the whole backpropagation for every training example again?
Yeah, so actually, I do not find very many related studies to investigate the how to determine the optimized data ratio between the general domain data and the medical domain data. So current medical large language models seems like they all depend on empirical study or just directly make the choices and set the data ratio. And yeah, so we cannot guarantee that the current data ratio we use is the best choices. But according to the performance evaluation results, seems like by incorporating more general domain data, so the knowledge forgotten issue can be alleviated. But this can also maybe make the negative effectiveness on the biomedical or on the medical domain task. So I think it requires further investigation. But we did some small experiments to investigate the knowledge forgotten issue between current models that conduct continual pre-training. And we found that the PMC LLaMA model use like the data ratio of 90:1 has the have the performance decreases on both general domain and the biomedical domain compared with its backbone model. And the Meditron model has the performance decrease in the general domain, but has the performance improvement in the biomedical domain. So we think it is better to have a balance between the general domain data and domain specific data.
Yeah, that makes sense. But also, if you could include it in the loss function, then you might not need any of the the training data.
Sorry, may I ask what do you mean like incorporate it into the loss function?
Potentially you could use KL divergence versus the original model so that the parameters don't get too far. Like this is what they did in the Instruct GPT paper during reinforcement learning. There's the loss function has part reinforcement, the reward, and part the original supervised fine-tuning model with KL divergence, so it doesn't drift too far.
Okay, you mean like I add some external layers like adapters to fine-tune to change the parameters in these adapters, but keep the parameters the same of the original models layer.
It can be an effort or not, but it would just be an extra term in the loss function.
Yeah, I think that's a very interesting topic that we need to explore.
We can.
Yeah, we can have further discussion about this. And I think too, since the LLaMA 3 has been released, so it may also very interesting to research the knowledge editing or other advanced technology that we can transfer learn the knowledge in existing continuous pre-trained models to the new models, so without repeat pre-training.
What do you see the next experiment you are going into based on this research, and how this? I think this is 1.4, and it's really setting up a model which is useful in biomedical and clinical domain. And then how could the other group apply your model?
Okay, yeah, that's really very interesting question. As we I discussed with Dr. Xu, our next step is actually to further continue pre-training LLaMA 3 models, because the LLaMA 3 just been released several weeks ago, and even the 8 billion model has shown very impressive performance when compared with the LLaMA 2 model 70 billion. So yeah, the next step, we plan to train 3 versions of models in future. The first one is to continue pre-training the LLaMA 3 model with the exact same data used in Me LLaMA paper. And then we will try to incorporate more clinical notes from University of Florida to further improve the performance of the model. And finally, we would like to let our model can be freely accessed by more people. So we plan to train a version of model without using mimic data or the EHR data from University of Florida, so that people can use it totally freely without the limitation of data usage agreement. And finally, we also plan to improve the long text handling ability of our models, because even we use the LLaMA 3 model, the maximum input token the model can handle is only 8K. I think this is totally not enough for many real-world medical scenarios. And for adapt our model use our model, I think the most intuitive way is you have a medical application scenario. If you have some training data, you can quickly adapt our model to improve its performance in your scenario by instruction fine-tuning it. Yeah.
That's great. I'm looking forward to the first adoption of your model.
Question. I have a question. So we use the mimic, but now we have constraints to release the data. You may use many different data from different sources, and later on maybe the copyright change or authorization change you want. You cannot use this piece of data anymore. Without retraining from the scratch, what are the possible strategies you can forget about this data?
I think that's really very interesting research topic that we can explore. Actually, I have short discussion with Han Lin before, and he conducted some research about machine learning, and I think it's very similar like knowledge editing. Basically, how you can edit the weight of the pre-trained model to let it doesn't leak the privacy data. Or I think another way that, as you discussed in the group meeting, is we can design some mechanism in the extra add in the output layer that like we can classify or determine whether the output responses leak the data we used during the pre-training and then revise it or rewrite it. And I think knowledge editing or machine, knowledge editing is very promising research direction. Like, and also very promising way to deal with the issue that we do not need to repeat continuous pre-trained model and directly transfer the learned knowledge in existing models.
Any other questions? Well, just thanks again.
Yeah, thank you.
Finish the food.